All right, so now we're going to be doing some calculations that involve frequency, wavelength, and energy put together. This can be confusing to kids. Yes, this can just be confusing. Like to some of you in this class, I know this is going to be like you're going to be like, no, I don't like this, and that's okay. But we're going to do the best we can. We'll walk you through it, do a couple examples, and that should be enough to get it to where you can do a couple of these. If it makes sense to you, well, awesome, great. Then honestly, you probably don't even need to watch this video. You can just do it and figure it out. I mean, you probably are. But then if there's others of you that are probably just like, no, I don't know what's happening. So watch this, take it to heart, be careful. Like just take your time, and like you'll be all right. So we have two. Remember, we have two formulas that we use that we've been using. So we have C is equal to wavelength times frequency. And then we also have E is equal to Planck's constant times frequency. So sometimes when you're doing calculations, you're going to have to relate the wavelength of something to the energy, or energy to wavelength. And the only way to do that is by using both of these equations. Now, thankfully, you will notice that they have something in common. They have frequency in common. So the way it's going to work, you will solve for frequency in one equation and then go plug it into the other equation and solve that. So it's kind of like you got to do two problems in one. All right, that's exactly like that. You're going to do two problems in one. But it's not like a fun get like two in one, like go to the store and buy something and you get two for the price of one. This is just you get two problems for the price of one problem. All right, so I can't do like coordinates and make that sound fun. That's just what it is. So it says, what is the wavelength? So we've got wavelength here. It says, what is the wavelength? So right away, you're like, all right, what's the wavelength? We're solving for wavelength. And it says that, now this is interesting. It does not tell you. It doesn't specifically tell you what this is. It doesn't say like, oh, this is energy. But you see J. You should see joules. Joules is code for energy. So this is energy right here. So that's energy. So how are you going to solve this? Well, again, you're going to do two parts of the problem. The first thing you got to do is plug this into this formula up here and solve for frequency. Then you're going to take this V, plug it in over here, and solve for wavelength. It's a multi-part problem. So to do that, let's just start. So we've got energy is equal to over here. So we want to solve for frequency now. So to do that, we're going to divide both sides by h, because we want to get frequency by itself on the side of the equation. So we're left with E over h is equal to frequency. Now remember, h is always 6.626 times 10 to the negative 34th joules times seconds. It's that constant value, Planck's constant. Remember that? All right, you will be given that, and you should just know that it exists, so you can use it. So we're going to plug our stuff in. So we'll do 7.65 times 10 to the negative 17th joules. Small number. But we're going to divide it by an even smaller number. Right, and this will equal frequency. Now, when you do this, do remember, please, that you need to divide using parentheses. So we're going to do 7.65 times 10 to the negative 17th divided by 6.626 times 10 to the negative 34th. Make sure, if you want, remember you can program in this. I mean, if I was doing this, I would just be typing in H, but I'm trying to cover everything for you on the video, so I'm trying to be nice. So our frequency in this case is, we'll say 1.15 times 10 to the 17th. Now, our J's are going to cancel, and we're going to end up with 1 second, so it's like seconds on the bottom, so it's 1 over seconds. That's our frequency. But that's not the entire problem. So what you'll do next, this is frequency. we are asked to solve for wavelength, so now we have to use our other formula. So now we know this. We're going to take this thing and we're going to plug it in right there. Now remember C. C, we know, is 3 times 10 to the 8th meters per second. You know that for sure, always. It's the same thing always. It's a constant value. I had to drink water. Too bad. So, and then there's Walter on the monitor over there. He's saying what's up to everybody. If you've been following these videos, you'll know that Walter is now going to become a character where, because I'm just talking to nobody and it's a little weird. There's Walter. He's a pumpkin on the monitor. Travels places around the world. Went to Shanghai last year. He thought it was cool. Anyway, so he's got a nice hat. I'll explain that someday to somebody if they ever want to know. But anyway, so you're going to solve for frequency, or no, you're going to solve for wavelength, and you know frequency. So we want wavelength by itself. So that means we're going to take frequency and we're going to divide both sides by frequency. And we are going to be left with C over frequency is equal to wavelength. Now it's just a matter of plugging everything in and solving, and then you're done. So we know that our C is 3 times 10 to the 8th meters per second divided by frequency, which is 1.15 times 10 to the 17th. So you'll do all this. Again, remember when you divide, put those in parentheses on the bottom, otherwise it's not going to work out right. So you want your C divided by almost forgotten myself. You're going to end up with about, we'll say 2.6. We'll just say 2.6. Or we can say 2.61 if we want to round up. Times 10 to the negative 9th. Now, these seconds are going to cancel, and you're going to be left with meters. So, your wavelength was 2.61 times 10 to the negative 9 meters. That's a lot for one problem. I will not expect you to do too many of these. Okay, I will not. I promise. You're going to have to do a few. Yeah. So there you go. Now, the problem does also say what type of electromagnetic radiation is this. So there is actually a second part of this problem. To figure that out, all you would do, you would need to look up and say, okay, what you'd basically say, like, what radiation has a wavelength of in this range, the negative 9th meters. And to do that, you would just go and look it up on the electromagnetic spectrum. I don't have it printed right now, but you would look it up, and then you would just identify it based on where its wavelength fell, and that would be X-ray, according to this. All right. Oh, and then let's do the next problem. All right. So, last but not least, the last example problem. Hope you're going to pay attention to this one. So we've got a bunch of stuff. First, there's a number in here. That doesn't mean anything. So it says the blue color in some fireworks occurs when copper chloride is heated to approximately 1500 Kelvin. K, we don't care about that. It emits blue light, blah, blah. All we care about is, boom, we got a wavelength. We have a wavelength of 8.30 times 10 to the second nanometers. It's a really fancy way of saying that your wavelength is 830 nanometers. Now, the problem here that some of you probably are thinking is like, what the heck is a nanometer? And that's not incorrect. That's a good question. So, like, what is a nanometer? All right, what are we going to do about that? So, a nanometer is something that you're going to have to convert because To solve this problem, you're going to have to do the whole thing again, where you're going to do two problems where you're starting in this case with wavelength, and the problem says, so it's saying how much energy. It wants energy. So in this case now, we got to look at this and say, like, all right, we're going to solve. We're going to solve for frequency again, and then we're going to take our answer and plug it in down here, and then solve for energy. So 2 steps, 2 problems. You know the drill. So to do this, we will work through it here. We'll make it work. But the first thing, the problem before we can do anything, is the speed of light, which is this. So it's 3 times 10 to the 8th meters per second. So our constant value is in meters. This is in nanometers. Those do not go together. So what I'm going to do is show you how to convert really quickly from nanometers to meters. It's not hard. It's just something you got to do. So you're going to have, we'll say we've got 830 nanometers. Dimensional analysis. Look at that. It's back. You should never forget about this. You'll put nanometers on the bottom. You'll put meters on top. Now, the conversion. This is the conversion. 1 meter is equal to 10 to the 9th nanometers. Nanometers are really small, like so small you can't even imagine how small. So 1 meter is equal to 10 to the 9th nanometers. So you'll plug it in just like that. You'll divide these. All right, and then you're going to want to write your answer in scientific notation. If you want to include 8.3 times 10 to the second, that's fine. It'll maybe make it even easier for you, because your answer is going to be this. It's going to be 8.3 times 10 to the negative 7th meters. All right, this value. This value is your wavelength. So now, the wavelength that we're going to use in our problem, all right, it is not 830 or 8.3 times 10 to the second. It is 8.3 times 10 to the negative 7th meters. Understand that if you start this problem with this value, it's not going to work. It's got to be with this value. All right. So now let's just go through, and now we just got to solve everything. But remember, this conversion is something you might have to do from time to time. So anyway, so let's do that then. So we've got our wavelength. Let's solve for frequency first. So divide both sides by wavelength, because you want to get frequency by itself. So our formula will be C over wavelength is equal to frequency. So then you're going to do, you know that C is the speed of light, so it'll be 3 times 10 to the 8th meters per second divided by our value for wavelength. That will be equal to our frequency. So you will do that. So you'll do the speed of light. I've got it programmed into the calculator. So we'll do the speed of light. Remember, I've got it programmed, so you can do that too if you want. It's much easier. Divide by parentheses. So our frequency is 3.61 times 10 to the 14th. And then remember, your meters are going to cancel, so you're left with just 1 over S. So your units are 1 over S, which is hertz, which is fine. And then, so now we know that we have our frequency. We want energy, though. It's really easy for kids to forget to do the second part of a problem, so don't forget to do that. And this is a long problem. This is like a crazy long problem. This is about as hard of a problem as I could imagine you having this whole semester. So, well, it's equivalent. I mean, you're not going to have many of them. So if you're like freaking out right now, being like, nope, don't worry. You're all right. You're okay. Tell me, you'll be fine. We can help you. You can just watch this video 100 times. And you can ask me about specific parts. And if you're watching this and you're not in my class, you can email me. And I'm probably not going to answer you, but you can try to email me if you're not in my class, and I might help you. Though realistically, not right now, probably. But maybe next year, when life is. Who knows? So anyway, you're going to put this in there, and you're now just going to say, all right, we got our frequency. Let's solve for energy. So we know our formula, energy is equal to HV. We know that H is Planck's constant. It is always 6.626 times 10 to the negative 34th joules times seconds. So that's our H. We know our V is 3.61 times 10 to the 14th 1 over S. So we did all that. That's going to be our energy. So you just keep it in your calculator like this. You can be really fancy, and you can just be like, oh, okay. So I'm going to multiply now and say this times Planck's constant, which I have also calculated already. And you get the energy, which is 2.39 times 10 to the negative 19. So our energy is 2.39 times 10 negative 19th joules. Our seconds cancel out. We're left with joules. And wow, that's a lot of work for one problem. And for those of you that have watched all these videos, I just did all 6 examples back to back to back to back. And I just recorded them separately. So I have a bit of a headache now. That's okay. I hope that this makes sense to you. Please let me know what questions you may or may not have about this. All right. Don't be freaking out if it does seem like a lot, because it is. This is not like, if this seems a little overwhelming, that's understandable. Just please don't hesitate to tell me. Okay. The end. Bye.